Hi, my name is Kamil, and in my session I will talk about patching of 100 OpenStack compute nodes with zero-day patch within 16 hours. And several words about. Oh, you can't hear. You can't hear me. You can hear me now. Even better right now. Okay, cool. So several words about me. I'm a cloud solutions engineer at Software-Defined Infrastructure Group, and I joined Intel in 2015. I'm a huge fan of emerging technologies and automation. And as Intel, we try to improve OpenStack and make it better. So how many of you have ever used OpenStack? Okay, and how many of you have a bad experience with OpenStack? Okay, quite a few of you. Okay, so let's talk about patching. What's patching? Who needs patching? So nowadays, where we have developers working on one product from multiple places and simultaneously, there are bugs, right? So humans make mistakes, and we are not perfect, and there will be always bugs. There will be always bugs. So some of them might be feature bugs, like some functionality is not working properly, and there are also security bugs that are a huge threat for you and your clients. So early patching lowers the risk of your systems to be compromised, and you shouldn't ever ignore patching, as this is a crucial piece of your software infrastructure management. So I pulled some data from the internet about most known zero-day vulnerabilities. You probably know them. First one is Heartbleed. Who heard about Heartbleed? Okay, quite a few of you. So this is an OpenSSL vulnerability that was introduced in OpenSSL in 2012 and was publicly disclosed in 2014. So that's a 2.5 year without being publicly noticed. And on a day zero, when Heartbleed went public, there were 500,000 servers vulnerable to this bug. So that's a huge number. And as an example of Heartbleed impact, there was a security breach at Community Health Systems in 2014 that exposed 4.5 million of data. And that's a huge number and trust loss from our patients, right? And the second one, Shell Shock. Who heard about Shell Shock? Cool. Family of Bash vulnerabilities that were publicly disclosed in 2014, but existed in Bash for over 25 years. So that's a huge amount of time. And 6 days after Shell Shock was publicly disclosed, there were 1.5 million of attacks recorded while using this security bag. So the question is, how would you apply a security patch in your OpenStack environment? And we had several requirements for that. In our OpenStack environment, our tenants were running regular workloads, so we actually had VMs in this environment. And we also assumed that the host security patch will require a host reboot to fix this issue. And also one of the requirements was that there cannot be any tenant workload downtime during the whole process, and the environment has to be patched in less than 16 hours. So how our OpenStack environment looks like. So we had 54 storage nodes with Ceph Dual installed on top of them. As for OpenStack, we had OpenStack Mitaka with 100 compute nodes and 3 controller nodes. About VMs, so we had 1,600 internal services VMs that performed the DB queries constantly, and also 2,400 public services VMs that were serving some content that was accessible from the internet. As a last piece, we had several load generators that were performing HTTP requests constantly to those public services VMs. So you will ask, how to do it in 16 hours with so much of you having issues with OpenStack? Probably the most known opinion about OpenStack that it doesn't work. So we had identified several scenarios that we want to test. First one, we are patching one compute node at once with one live migration during host evacuation. Second one, we also were patching one compute node, but with multiple live migrations during host evacuation. Third one, we were patching multiple source hosts, but only one live migration per compute node during host evacuation. And the last one, we were patching multiple compute nodes with multiple live migrations. We also wanted to see the influence of several live migration features we have available. First one is tunneling, and the second one is auto-converge. So let's move on and talk about tunneling. What is tunneling? So in typical live migration scenario, data is copied between two hypervisors. Tunneling is a strong encryption mechanism that leverages libvirt RPC protocol capabilities. And because of that, there are extra data copies involved between both in source and destination host, as the data is moved between hypervisor and libvirt, not as in typical live migration where the data is moved between two hypervisors. About auto-converge. And in typical scenario, you have a VM with memory write-intensive workload, and in live migration without auto-converge, it will most likely fail in OpenStack. Auto-converge is a feature that dynamically throttles down the guest execution speed. So as the time advances, auto-converge will throttle down the guest CPU to allow the live migration to finish. Of course, there are some workloads that won't benefit from this feature, as auto-converge assumes that the throttling of guest CPU will also effectively throttle down the guest memory write speed. So one of our requirements was that we are pretty lazy and want to automate all the things that we use. So we went with one deployment host that we had Ansible installed on top of that, and we automated everything, the whole process with Ansible. So we used Cobbler to provision the bare metal servers. In our case, that was 157 servers. We used Ceph Ansible playbooks to deploy the Ceph Jewel on top of our storage nodes, and OpenStack Ansible playbooks to deploy the OpenStack Mitaka on top of our compute and controller nodes. And as usual, it never goes as planned. There were several issues with deployment phase. First one, Ubuntu 16.04 was not supported by OpenStack Ansible. It is now, but in that time, it wasn't. So we had to move on and roll back to 14.04. And because of that, several packages were outdated. Most QML libvirt packages had several improvements to live migration process in newer versions, but we decided just to go what was available in Ubuntu 14.04. Another problem that was a huge issue for us for Ansible scripts that we used is that the default number of instances returned by Nova API is 1,000. And since we had 4,000 VMs, we were unable to just get the whole list of VMs that we wanted. And the Ansible library Shade was not supporting the paging feature that Nova provides. So we just modified the OS API max limit variable in Nova configuration to solve that. As the next issue, default OpenStack Ansible live migration configuration just doesn't work. It assumes that there will be a TLS encryption communication will be using TLS, but it never configures that on our hosts. So we just disabled the TLS and used SSH instead. And the last issue, we were unable to create Cinder volumes due to large amount of Cinder timeouts. And our VMs used huge QCO images, and because of that, we couldn't use Ceph copy and write feature that only works with raw images. So we just increased the Cinder volume creation timeout. So let's move on from this theory and get to the fun things. The first scenario we performed was patching of one compute node with one live migration during host evacuation. We had tunneling enabled and just for a warm-up scenario, we had all VMs being idle, so no workload was applied on the VMs. And the total patching time was 33 hours and 7 minutes. And that's twice as much than what we expected, right? So our requirement was to go in less than 16 hours, and this is twice as much. So we started to think, what went wrong with this scenario? How can we improve the time? We had monitoring deployed on all of our hosts and VMs, and we noticed the strange thing that the migration data speed was less than 2 gigabits per second. And we had 10 gig NICs in all of our servers. So we just applied the load and it cannot go even better, even worse, so we just apply the load and see what will happen. And the first live migration just failed completely. It timed out. Even if we increased the live migration timeout to 15 minutes, it just failed. And this happened because of the virtual machine changed memory pages faster than host could transfer that to destination node. And we started looking for a guilty one, and we found out that the tunneling was the actual bottleneck for that. So let's remind ourselves what tunneling is. In typical live migration scenario, you just copy data between two hypervisors, right? And libvirt tunneling is a strong encryption mechanism that because of that, you have extra data copies between libvirt and hypervisor, right? So there's a middle layer that might slow down the whole process. So we just disabled the tunneling, and this lowered the total patching time to 17 hours and 48 minutes, which is much closer to what we wanted to achieve. And I won't go through all the scenarios because you're tired and you'll fall asleep, and you'll probably just kick me out from there. And so we performed the 16 different scenarios during our tests, and the lowest time achieved was 2 hours and 55 minutes. And this time was achieved in a scenario with 3 compute nodes being patched at once with 3 concurrent live migrations during host evacuation. But there's more. It never goes without problems, right? So in this scenario, we noticed that RabbitMQ connection to RabbitMQ were failing a lot during the live migration. And this caused something called ghost virtual machines. So several of the failed VMs were running on a completely different compute node than Nova was reporting. And because of that, there was a resource mismatch between Nova and what was in reality used. We even tried to live migrate the failed VMs to the correct compute nodes, but then Nova just went crazy and said, okay, there's a VM disk on a destination node, I won't do that. So we had to shut down the VMs and restart Nova Compute services. And in our requirements, we had a note that there cannot be any tenant downtime, right? So this scenario cannot be used. So the lowest time achieved that with all VMs being successfully migrated was 5 hours and 40 minutes, which is pretty good, I guess. And this time was achieved in a scenario with 3 compute nodes being patched at once with 1 live migration to the compute node doing host evacuation. With our test, we tried to address several OpenStack enterprise gaps, and we mainly focused on high availability for tenant workloads. And the features we wanted to test out were live migration and host maintenance mode. To conclude, the first conclusion, tunneling performance is poor. Never use it. It doesn't work. Libvirt encryption mechanism is single-threaded, and this slows down the live migration process by up to 80%. By OpenStack Newton, tunneling was a default live migration flag, and based on our tests, we decided to apply the patch that will remove this flag from default flags, and it was merged in OpenStack Newton. So there is no performance bottleneck starting from OpenStack Newton. As for autoconverge, it was never triggered. The live migration process was advancing so well that there was no need to throttle down the guest execution speed. One thing to remember, be careful with a number of parallel live migrations you are performing. In our case, in scenario with where you had 2 hours of total test time, we had 9 live migrations at the same time. So this caused our RabbitMQ to just go crazy and fail every time the live migration was performed. So in our environment, the most optimal number for concurrent live migrations was 3. And the last conclusion, apply security patches as fast as possible. Always assess the importance of security patches and apply them as fast as possible and as often as possible. Ignoring them or delaying the patches may result in huge losses. Either these are data loss, money loss, or just pure loss of trust from your customers. And as we all know, regaining trust of your customer is very hard, right? And last one marketing slide. So if you're a technology freak as we are, and you would like to work at Intel, come talk with us. Maybe we'll have something to offer to you. Thank you.
Okay, we have time for, plenty of time.
Plenty of time.
Exactly, for questions and answer session. So, there's a question in the back. You want me to run?
If the RabbitMQ was the source of the issues for more concurrent live migration, did you consider update RabbitMQ instances run on node what they are installed? Like what exactly what was the source for that RabbitMQ? To high load or?
There were too much connections for the RabbitMQ, so as a principle of our test, we went with the default configuration that most of users will do, so no RabbitMQ tuning, etc. And with default configuration and 9 live migrations, it just fails. Even VMware doesn't allow for 9 live migrations at once, I guess.
Thank you.
Another question? Okay.
So the issue with a mismatch between what Nova and all the OpenStack things and what really is on the system is a quite common problem. Did you investigate some solutions, to have some kind of transactions to get rid of this problem?
We at Intel have a Nova core right now, which is working on this problem. Because due to the results of this test, the problem was already noticed, and there's a fix incoming, I guess, soon.
Okay. One more.
Long walk.
Yeah, exactly.
I'd like to clarify if I understood it well. You had a problem with tunneling between 2 clusters, right? Or
No. Tunneling is a libvirt live migration feature that encrypts the data that is copied between 2 hypervisors. So the data, there's a middle layer in this communication, and there are extra data copies involved. So the whole process is much slower. There is no tunneling as it might, as it look like, but it's a pure libvirt feature.
yeah, and couldn't you just disable the encryption over this?
I would suggest
feature?
using alternative methods, securing it with different kind of solutions, but never use tunneling because it's single-threaded.
So in the end, you made a few separate migration for each rack space separately, right?
I would suggest to use the dedicated live migration network for that, VLAN, etc.
Okay, thank you.
Okay, anyone more questions? Give me a sec.
So when we can expect all the patches or all the fixes apply to OpenStack? Is it next cycle or Okata cycle? Do we know?
I guess so, yes. This is a major problem, and we have a team that is working on to improve the live migration. So I guess Okata is a good guess, but who knows what will happen in the OpenStack community, right?
If there are no more questions, officially we can say thanks a lot. Great presentation.